Greetings, my name is Jordan Ochoa. I'll be introducing our work titled Automatic Diagnosis of Diabetic Retinopathy from Fundus Images Using Neuroevolutionary Algorithms. To start off with introduction, diabetes is a widespread disease that can damage blood vessels in the retina and lead to a loss of the visual system. To combat this disease, called diabetic retinopathy, images of the fundus of the retina are commonly used for the diagnosis of the mentioned disease. To aid us with this task, deep learning is employed for detecting the disease. The deep learning method's performance, however, are highly dependent on the optimal configuration of the hyperparameters. In this article, we propose the use of neuroevolutionary algorithms to optimize the hyperparameters of set models. Diabetes mellitus, also known as diabetes, consists of a heterogeneous group of metabolic disorders mainly caused by the presence of high blood glucose levels. Over time, diabetes can lead to a visual impairment called diabetic retinopathy, which is a degenerative eye disease that progressively damages the retina. Therefore, early diagnosis is a key factor in order to prevent the disease progression and permanent damage to the vision system. Ophthalmologists often use the retinography method to obtain color images of the eye fundus, including the retina and other structures. This also allows them to detect lesions in the eye so they can detect the disease. Currently, diabetic retinopathy is considered the leading cause of visual loss in the world, with approximately 93 million people diagnosed. Considering the increasing worldwide prevalence of diabetic retinopathy, there is a need to optimize the detection procedures of it. Therefore, it makes sense to propose the optimization of computer-assisting early diagnosis of the disease. In the figure, we can see multiple examples of the retinographies that are employed to detecting the disease. Following, in this section, I will describe the dataset and the methods that are employed by our proposal. The dataset that was employed in this research corresponds to over 1,000 color fundus images collected at the Department of Ophthalmology at the Hospital de Clínicas. This dataset is also publicly available for research, and as mentioned, it consists of eye color fundus images with over 1,000 images. This dataset is divided into two different sets. We have the training validation set and the test. The training validation is used during training, and the test is used to obtain the performances of the classification power of the models. The images are classified between the presence of diabetic retinopathy and the absence of diabetic retinopathy. Deep convolutional neural networks have demonstrated their effectiveness in tasks related to feature extraction and classification. Nevertheless, one of the main drawbacks related to very deep networks is the vanishing gradient. In this case, the vanishing gradient causes the learning of the neural network to be slowed down to a halt. To avoid this, residual neural networks have been proposed, which applies some optimizations and shortcuts in the network architecture, which manage to reduce the overfitting of the data and also eliminate the vanishing gradient problem. In this figure, we can see that residual neural networks are composed of multiple layers that learn different characteristics of the images. For example, the lower layers learn to distinguish light from dark pixels, while the next layer can detect edges, and so on. Those features can then finally be combined, and the final output is obtained. In the case of detection, it would be the case if the disease is present or not. Another method that was employed in this proposal was the transfer learning and the fine-tuning processes. The transfer learning process allows us to transfer knowledge from one domain to another. This is achieved by using pre-trained models for similar tasks. This approach is commonly used in the fields of computer vision and natural processing. The main advantage of using transfer learning is that it requires less time to complete, and it is not necessary to employ a large dataset. In the transfer learning procedure, the last layer of the network is readapted while the remaining configuration of the network stays the same. The configuration of the multiple layers of the learned model are retrained. It is based also on the transfer learning, but it readapts the model to a higher degree. Another method that we employed is that of the evolutionary optimization. As mentioned before, the hyperparameters of the model need to be optimized. The evolutionary algorithms, which are inspired by the process of natural selection, allows us to obtain the optimal solution. In this research, the main objective is the optimization of the network architecture to achieve a higher binary classification accuracy for diabetic retinopathy diagnosis. The essential component is the genetic algorithm, which is the evolutionary algorithm selected to perform a single objective optimization. This allows us to obtain the optimal individual from a set of multiple parameters. The optimization procedure is presented. We start off from a random initial population consisting of different neural networks with different hyperparameters. Each individual is then subjected to a fitness evaluation. This is obtained from the accuracy performance of the classification. Later, those individuals are subjected to the crossover, mutation, and selection methods, which are responsible for creating a new generation of individuals. Each generation is better than the last, therefore, once we reach the stop criterion, the optimal solution is found. In this case, the stop criterion is reached when the maximum fitness has converged, meaning that the maximum fitness hasn't changed in the previous generations. In the process, the dataset of eye-fundus images is used to train and evaluate the neural networks. The training validation sets are used during training, and the test set is used to obtain the final accuracy value used as the fitness. In the following table, the parameters of the optimization procedure are listed. The population size consisted of 100 individuals, the maximum number of generations was that of 30, the chromosome length is 4, corresponding to 4 hyperparameters, the mutation probability was that of 5%, and the crossover probability was that of 75%. In the following table, we have listed the results obtained by each neural network. The first 4 models were tested at first to select a baseline. The ResNet 50 was selected because of the balanced performance in training time and accuracy. It can also be seen that the optimized solution obtained an improvement in the accuracy, sensitivity, and specificity metrics. In the following table, the optimized parameters of the neural networks are listed. We can conclude from the results of the experiment that the optimized solutions have shown a substantial improvement in performance according to multiple performance metrics. The optimized solution fits the minimum sensitivity of 80% and specificity of 95%. This was established by the UK screening standards for diabetic retinopathy. Future work will focus on multi-class classification and optimization of other neural network architectures.